Hi there and welcome back again to our video lecture for the course ENSC106, and in this video we are still in our first topic, which is the review of static concepts. But right now, instead of going through sample problems in 3 dimensions, we'll move on now to the geometric properties, because after all, when we're dealing with stresses and strains, we are dealing with forces. Okay, not only with forces but also with geometric properties such as area, moment of inertia, and things like that. Okay, so right now we'll discuss the geometric properties. Okay, so first geometric property that we'll consider is the cross-sectional area. Okay, so the symbol that's often used for cross-sectional area is just simply A, and what that means is it's the area at the cut section. Okay, so for example, I have this shape right here, and then I want to cut somewhere right here, somewhere along the length perpendicular to the longitudinal axis. Okay, so if this is the section plane, then the area that I'll get is this area. Okay, so I'll shade this with this black color, and therefore the area right here would be this one, this area, a circular area. Okay, so for a circle, the area is just simply if this is, let's say this is D, this is the diameter D, so that means that the area is just simply A is equal to pi D squared all over 4. Okay, another one is, for example, I still have this same object, but the section plane will be oriented in this position. Okay, so if that's the case, then the cross-sectional area would be this area. Right, so drawing here, if this will be our let's say this is our height, for example, h, and then this is our diameter, right? So therefore the area is simply the area of the rectangle, h times d. Now it's also possible for other types of stresses that the area is not just a planar area, I mean in just a straight plane, but it's also possible that the section I mean the cross section, or the section plane is a surface, I mean a curved surface. Okay, so for example, right here, this will be my curved surface. So it's hollow inside, right? And if that's gonna be the case, then what I get is something like this. So this will be my cross-sectional area. Now if I'll draw it here, it will look something like this. Okay, so this is our thickness and this is our diameter, for example. Then the area would be A is simply pi d, the circumference times the thickness. Okay, times the thickness. Okay, so that's all for the cross-sectional area. Now let's move on to another geometric property, which is the moment of inertia. Moment of inertia, and more specifically we are referring to the area. Okay, area moment of inertia, because there's another concept of moment of inertia in dynamics, which includes the mass, and that's mass moment of inertia. But for us here, we only consider the area moment of inertia, and the symbol is simply I. Okay, and this moment of inertia actually comes into play when we are dealing with bending. With bending and for torsion, actually there's another or there's a specific moment of inertia for the torsion. Okay, anyways, this moment of inertia is actually the second moment, right? Second moment of area. Okay, so when we say moment, right, when we say moment, just think of it as you can think of rotation. Okay, so imagine that, for example, I have this cross-sectional area, and I'm going to draw this in 3-dimension. I'm just going to draw this oriented in 3-dimension. Okay, and let's say this is my my cross-sectional area. Okay, so in this cross-sectional area, let's say we have this centroid right here. And what if I'm going to right? So, for example, this is our x-axis, right, and this is our y-axis. Now what if I'm going to rotate this area along x-axis, or I'm going to rotate this area along the x-axis or along the y-axis? Okay, so if that's the case, that's the concept of the moment of inertia. However, the moment arm that I'll be considering is the square. Okay, so this is actually the a more specific term for this is the second moment of area. Okay, so that means that there's also another moment of area, which is the first moment of area, and that's not what we're talking about. So this moment of inertia is the second moment of area. Okay, so in mathematical expression, we can express this moment of inertia. If we rotate this along x, we have this expression as y squared times dA, right? And for the moment of inertia along the y, this is x squared dA. Okay, so let's focus right now in the contents of these expressions. Okay, so this is our moment of area. And by the way, as I have said, that this moment of inertia comes into play for when dealing with flexure or bending, let's say the bending stresses. Okay, so somehow it's like a resistance to let's say to bending or torsion, or simply rotation. Okay, so the more area away from the neutral axis, actually that's more resistant. Okay, so right here, this is our expression I sub x. That means that we can have moment of inertia along x, or we can have also moment of inertia along y. So here for along x, you would notice that this is our area, right? This is our area, and this is the moment arm, something like a moment arm, but the technical term there is the distance from the axis of rotation to the centroid, right? to the centroid of the occupied area or area concerned. Okay, so that's the basic mathematical expression. But in terms of significance in practice, now consider we have a beam like this, and we have another beam positioned in this position, right? So we have the same cross-section, and let's say we have the same material properties, we have the same dimensions. But right now, what I want is, what if I rotate this, and let's say I rotate this along the x-axis. So which one is more stiff? Okay, so for example, I have this ruler right here, and I'm going to bend it. What if I'm going to I think this should be it. Alright, so if I'm going to bend it in this manner, so this is much easier as bending it in this manner, right? So I can't, or it's really hard to bend it. So just like, for example, this is my neutral axis, or the axis of my rotation. So if I bend it like this, it's hard, right? But if the axis of rotation is here, and this is the position of the cross-sectional area, it is much easier. So what that means is that if you have more area, away from the axis of rotation or the neutral axis, that's gonna be more stiff. Okay, so somehow that's a measure of flexural resistance. Okay, so as I have said, there's gonna be two moment of inertia, because I can have a moment of inertia along x, and I can have a moment of inertia along y. Okay, and this is integral of x squared dA. Okay, so whenever you would encounter this integral sign, that means that that's the general, let's say, the general way for obtaining the moment of inertia. Although there are also another way, like from the tables. So you can find moment of inertia from the tables. Right, so that means that if it's from the tables, then that refers to regular shapes, and this one is irregular shapes. Okay, so example is this one. Okay, so you can actually find this in the textbooks and many other references. Like, for example, we have a rectangular shape. Then what's our moment of inertia along x and moment of inertia along y? Okay, so right here I only included the moment of inertia if our axis of rotation is along the centroid. Okay, so if it's not along the centroid, then that's going to be a different equations, and that's why sometimes in some texts you would also find other values for I sub x, but that means that one value refers to the moment of inertia when we take the axis of rotation along the centroid. Okay, so right here for a rectangular shape, it says that our moment of inertia is 1/12 base times height cube. Okay, so this is our base. So take note, we are taking rotation along the x-axis. So we are rotating this area along the x-axis. So with respect to this x-axis, the base is this one, right? And the cube term refers to the height. Okay, so that's the height. Now if you take the moment of inertia along the y, this will be our base. I mean the the first degree term is the height, and the third degree term is the base. Okay, so that's it. Okay, what else? Now, with respect to the centroid is just simply the midpoint between the base, or the midpoint of the base and the midpoint of the height. Okay, so you're gonna have, let's say, along the x bar, and then the y bar is just simply h/2. Now, for a triangle, the centroid is somewhere one third. Okay, let's say this is the base, that's gonna be 1/3. Okay, and also right here, that's gonna be 1/3. Now, for the moment of inertia, we have 1/36, and also take note that this moment of inertia is the moment of inertia taken, where the axis of rotation is along the centroid. Okay, so that's 1/36, and for a circle, we have 1/4 pi r to the fourth. Okay, so since this is asymmetrical, not just symmetrical but rather doubly symmetrical shape, meaning that either in x or in y direction it's the same, so that's why the moment of inertia along x and along y are it's the same. Okay, and there are still many other shapes, equations for the other shapes you can find in the references or in the textbooks, but that's the main idea. Okay, what else? Now, sometimes, as I've said here, we can obtain the moment of inertia in the tables, right? For the regular shapes. In regular ones, like for example, you have a parabola, or maybe some other higher degree curves or things like that. But sometimes we don't want to, or sometimes the axis of rotations that we want is not along the centroid. Okay, so what I mean by that is, for example, instead of rotating, let's say still along the x-axis, but instead of rotating that, I would like to rotate somewhere here. Okay, so let me draw it here. So let's say I have an arbitrary body or area, and let's say the centroid is right here. Okay, and this is my x and y axis. Right, so this is the original x and y axis along the centroid. Okay, so let's say I take I guess I just rather write this. Now, what if instead of rotating it here, let's say along the centroid, what I want is to rotate it, let's say somewhere here, right? And let's say this is x prime, and then this is y prime. Okay, so if that's the case, what's gonna be the moment of area? The moment of inertia. Well, what's gonna be that equation? So if that's the case, if we have a different location of the axis of rotation, then we are going to use the parallel axis theorem. So what that means, or what that explains, is that if the axis of rotation is not at the centroid, that means that we must use this theorem. Okay, and let's say we are going to take the moment of inertia along x. So what that means is I sub x is simply the moment of inertia along the centroid. Okay, so I put a bar on top of this ix, just to designate that this is the moment of inertia along the centroid, okay, plus the area times the distance. Right, so right here we have a moment of inertia, right? And that's the moment of inertia along the centroid. And we need to take another moment of inertia right here, which is this this term. Okay, so the total area times the distance from the new, or from the specified axis of rotation to the centroid. Okay, so this is it, a times y squared, which is just simply this is also a moment of inertia, an equation of the moment of inertia. Okay, so this is also true for I sub y. Okay, so right here, let's write this is the total area, or the area, just simply the area, and then this one, the y, is the distance from the axis of rotation to the centroid. All right. So now let's have a problem, a sample problem for this moment of inertia. Okay, so this problem is our problem 1.6, which is taken from the textbook of Fibular, and that's example 10.4 and page 523. Okay, so the problem says that we are to determine the moment of inertia about the x-axis. So here is our shape. We have a shape, a composite shape made up of a rectangle and a circle. Okay, and whenever we have a composite shape, we don't actually need to go through the integration. All right, so this is our x-axis, and we are going to take the moment of inertia. And so the distance, we have a base of 100 mm, and we have a height of 150 mm, and this one has the diameter of 25 mm. That's the radius. Okay, and here is our centroid, because the centroid of the circle is just simply the center, and the centroid of the of this one, of the square, is simply at the midpoint. Okay, so for our solution, okay, so for the first step is to draw the shapes separately. Okay, so what that means that I can draw this square, or I can take this simply the square minus the area of the circle. Okay, so we have this square or rectangle, right? And let's say this is our x-axis, and right here we have this shape. Now for the dimensions, so this is 100 mm, and this one is 150 mm, and the distance from the axis to the centroid, this is 75 mm. Okay, and for this one, the distance from the centroid to the axis of rotation, this is 75 mm as well, and the radius is 25 mm. So we can actually take the moment of inertia I sub d, the total moment of inertia of this section is just simply I sub d of the, let's say this is our area 1 and this is our area 2, so I sub 1 minus I sub 2. Okay, so this is our working equation. Okay, so now let's solve for I sub 1. Okay, so solving for I sub 1. Okay, so I sub 1 is, you would notice here that the given formula is from the centroid. So if we take axis of rotation along the centroid, this will be the formula. However, we are not taking the axis of rotation along the centroid, but rather we are taking it right here. Okay, so we need to use the parallel axis theorem. Okay, so I sub 1 is just simply the moment of inertia, right, along the centroid plus the area times the distance, times the square of the distance. Okay, so what is Ix at the centroid? This is 1 over 12 bh cubed. 1 over 12 bh cubed plus, what is the area? This is simply b times h, right, times the distance y squared. Okay, so now let's substitute all the values. We have 1 over 12 times our base, right? Our base, this distance is just 100. Okay, 100 times our height, this is 150 mm cube, right? Plus this b times h, this is just 100 times 150 times the distance, the y distance, this is it, from the axis of rotation to the centroid. This is 75 squared. Okay, so if you do the math, what you get is 112.5 times 10 to the 6, and the unit is mm to the 4th. Why? Because this area, so this is meter squared or millimeter squared, and this one is unit of length, but you square that, so millimeter squared again, so you multiply that, what you get is millimeter to the 4th. Now I guess I have to continue this problem in the next video.